All right. So a linear system of two equations with two variables is any system that can be written in this form. AX plus BY is equal to H So basically you have your linear, your actual variables on the left, and you have some constants over here, okay? So where any constants can be 0 with the exception that each equation must have at least one variable. So there's a couple of ways to solve these. You can do it graphically, which I think is the lamest way. I do not recommend that. Algebraically, which includes substitution or elimination. So let me write that down here. Talk about solutions. A solution of a system of linear equations consists of values for the variables that are solutions of each equation of the system. The solution is represented as an ordered pair. So let me give you a visual as what the heck that means, right? Because right now it's like whatever, correct? Like a bunch of words. So let's see. Yeah, here. On an example real quick. Okay. So use my grapher so you can see. Okay. All right, so okay, can you guys see the graphing thing? I assume so.
We can see it.
Thank you. All right, let me type these guys in real quick. What the heck? Okay, let me zoom in. So these are two equations. So if you think of this as one system, the solution to the entire system is basically the point where they intersect. So you could graph them and use Desmos to help you find the solution. So the solution to this system is 3, 2, because it satisfies both equations at the same time. So if I plug in 3, 2 for x and y, you will get some sort of equality. If you plug in 3, 2 here, you will get equality again. That shows you that yes, it is a solution to the system. And that's what they meant by ordered pair, x and y, two values, right? The point. Okay. All right. But they're not always. I mean, if you use Desmos, graphing might work all the time because it's not too bad. But if you use a graphing calculator, finding the intersection point could be annoying. Okay. Um, but let me give you 3 scenarios when you're solving, because it's not always. There's not always a solution. There's 3 things that could happen. Okay. Solving system graphically. Well, let me rephrase that. I don't like how that sounds. So 3 different scenarios for solving a system. And remember, a system does not have to be 2 equations. It could be 4 or 5 or whatever. But in this section, we'll just do 2. Okay. And actually, it's an interesting idea. System of equations are used as part of the main idea for linear algebra, also called matrix theory. So you have like millions of these with millions of variables, which is what is basically used within your Google searches. So when you search something, you'll have it'll automatically calculate millions of x, y, z all the way through whatever, right? X1, X2, X3. They don't usually use alphabets, right? But solving a huge system of millions of equations will find you a specific website or an approximation as to what you might want. So it's a really complex thing. So every single day you search something, there's these system of equations working in the background. There's a linear algebra. Of course, you don't think about it, but it's there, right? Anyway, so that's why these things are. This is the most used topic in mathematics. It's matrices and linear algebra. Okay, so 3 scenarios. Number 1, you could have one solution, also called a unique solution. And it looks like this, like the one we just did. We had one number where they intersected, right? 2 lines going somewhere, intersecting like there, for example. So this is called one solution or unique solution. They call the system is consistent. It's another word they use for having a solution. System is independent, meaning there's just one solution. Okay. Now let's talk about number 2. Sometimes there's no solution, meaning they don't intersect. You can have 2 lines doing this. See how they're parallel to each other? So when this happens, there's no solution. This is also called inconsistent. Whatever. I guess I don't need. I should be consistent. System is inconsistent. System is independent still. Okay. So if you were to try to solve this system, you would get either something that's false, a false statement, or if you graph it, you'll see that the lines never touch. Okay. Now the third scenario. Infinitely many solutions. So if you have a line that is on top of the other line like this, then you will have infinitely many solutions because they intersect everywhere. So you also call this system technically consistent because there is a solution. It's just that there's infinite of them. Infinitely many consistent. But it's also called a dependent system because the two lines are really one and the same. They're just scaled differently. One might be multiplied by an extra value or something. Okay. So those are the main ideas. Now let me show you how to solve it with a calculator. If you have and I'll show you also a website too. But I'm not going to require, even if the question says do substitution, I'm not going to make you do that. I feel like that's not that important. So let me give you a question real quick. Here, this one. I'm gonna be very as leaning as what's the word is as generous and lenient as I can for the final exam. So you can use whatever you like. Okay, example 1. X plus 3y is equal to 9. 4x minus 2y is equal to 8. Okay. So you can graph them and just see, right? Which we did that earlier. These are the same equations, but if we do it algebraically, if I call this equation 1 and 2, that way you can distinguish them. If I say, you know what, I want to add these functions straight across, with these lines, I mean, and try to cancel a variable. So this technique I'm about to use is called elimination. So I'm going to multiply equation 1 by -4. So every single term will be times -4. So -4x minus 12y is equal to -36. 4x is the second one, so I'm going to write it again. Minus 2y is equal to 8. So this is still 1 and 2. Right? Since it's an equation, you can always multiply both sides by whatever you like, except 0. So now you add them, right? Negative 4 plus 4 is 0. Negative 12 minus 2 is negative 14y. Negative 36 plus 8, that'll be a negative 28. So this technique I just used is elimination. So I eliminated x. So now I have negative 14, y equals to negative 28. So divide by negative 14. Y will be equal to 2. So I solve for y. Now, once you have one of them, you just plug it into the other, right? So now plug in y equals 2 into equation 1 or 2, doesn't matter. You pick. I'm going to pick equation 1 just because it looks easier, maybe. Doesn't matter though. So I'm replacing y with 2. So that'll be this. This will be that. So now I have x and I have y. So the solution to the system is 3, 2, which we already knew from the graph, right? Let me move this camera a little bit. We already knew, right? So if you use elimination, you can graph them. Substitution, I don't recommend. You can also use matrices, which is the one I prefer. You can change this into a matrix. The idea behind matrices is you make sure they're in order, x's, y's, and constants. So there's a column of x's, so 1x and 4x, right, for these guys. 3y and negative 2y, 9 and 8. Okay. So this is the x column, y column, constants. That's where these numbers came from. So what you can do is putting into your machine by going to second, go second, and then go to x inverse. There's a little matrix up there. Once you're in there, you choose the dimensions, and you gotta decide, okay, what is the dimension of this matrix? It's always row by column, excuse me. So that's gonna be 2 rows, 3 columns. The dimension is 2 by 3. So in here, you put 2, 3. So 1, 3, 9, 4, negative 2, 8. So put it in there. Once it's in there, you can tell it to solve for you. You can go back into the matrix menu, go to math, go all the way down to RREF, go back in there and pick the one you made, which is under A. And it'll solve it. See? So x is equal to 3, y is equal to 2, which we already knew, right? So you can use your graphing calculator, you can use elimination, you can graph them on decimals. You can use whatever you like.
Can you do it again on the calculator?
Yeah.
I was trying to follow this stuff. Thank you.
Yeah, let's do it again. Okay. So hit second, and then press the X inverse button. So see it says matrix in blue right there. So this takes you to the menu for all matrix stuff. So all these are matrices you can save. Here, sorry, I'm off the screen there. So 1, 2, 3, whatever, those are all saved matrices. So I'm gonna go edit the first one, press enter, and then it asks me, okay, what's the dimension? So it's a 2 by 3. So then I go in there and just type it in the way I wrote it. X columns, Y columns, constants. So 1, 3, 9, 4, negative 2, 8. Once they're all entered, just hit second mode. It lets you get back to the main menu. Now we go back to the matrix menu by doing the same thing, second and X inverse. and then you go to math. All the math operations in here are only for matrices. So RREF is the one you want to use to solve a matrix. It's way at the bottom. You press enter, then it's waiting for you to go get a matrix. So I go back in there and then choose the one you made. I'm going to choose the first one. That's the one I edited. I changed in it. Then just press enter and that'll solve it. So when you see this, right, that means that x is equal to 3 and y is equal to 2. If you get something that doesn't make sense in here, like for example, if you get 0, 0, and then a number, that would be a false statement because 0 does not equal a number. 0 is 0, right? So that would give you a hint that there is no solution. And if you graph them, you would see that they are parallel. Okay. Now let me show you, I'm not going to waste time on this, but let me show you how it looks like with substitution. So this is the notes that the question that I chose from the notes that's posted. So they use substitution, which I don't really care for, but this is how it works, right? So they take equation 1 and 2, and they choose one to solve for x. So they chose 1, and they solve for x. So they're like, okay, move the 3y over. So x is equal to negative 3y plus 9. So they plug this guy into the x for the other equation. So that this is now x that goes in there. Distribute the 4, and then you solve for y. So all these next steps are just solving for y. Eventually you get to y is 2. Again, plug that into 1 or 2, doesn't matter, and you solve for x. So x is 3, 2. So you can do substitution, you can graph it, or you can do elimination, or you can use a matrix. Let me show you another way to do it using an online solver that's pretty decent. Let's see if I can find it real quick. Matrix solver. Yeah, I use this guy. I'll share the link down here with you. Sometimes when I'm lazy, I don't want to use my calculator, I'll use this website. I'm going to share the screen to show what it looks like. Okay. Okay, so our matrix is a 2 by 3, 2 rows, 3 columns. If you forget the order, just think RC coda, row by column, R by C, 2 rows, 3 columns. So hit set matrix, and then you type in the numbers. So our numbers were 1, 3, 9, 4, negative 2, negative 2, and 8. So solve. So it says x1 is 3 and x2 is 2. So they use x1 and x2, which means x and y. They just use these guys because there could be like 20 of them, right? It could be a giant matrix. So after a while, we run out of letters or alphabet. So it's best to just stick with x1, x2. It doesn't matter though. Okay. So you can use that if you like. And I posted a link in the chat box. Anyway, so that's 5 different ways. I don't remember. I already forgot, but it's all good. Let's do another one. Let's do one that has no solution or has an infinite number. Yeah, that would be better. Okay. All right, so this next one. X plus 3y is equal to 9. 4x minus 2y is equal to 8. Let me double check here. One second. I think it's the same question. Why did I write that again? 4y, there's 2y, 8. Yeah, sorry, that's the same question. Let's pick a different one. Yeah. Okay. So on this one, we're going to see there is a solution. Okay, so you can graph first to see what's going on. Let's go ahead and do that. Share grapher. So delete all this. So 3x minus y is equal to -4, -6x plus 2y is equal to 2. So you can see right away, right? They never intersect, ever. So there will be no solution. So if you try to solve it, you'll get an error. If you using a calculator, if you use elimination, you'll get a false statement, or substitution, same thing. Let's see here. Let's try the solver over here. See what it looks like. So we still have a 2 by 3, right? Let me go ahead and first change it into a matrix because I need it in matrix form. So this will be, right, so the x column, 3 and -6. The y column, -1 and 2. Constants, -4 and 2. Okay, so now I have it. Let's go ahead and type it. It'll be 3, -1, -4, -6, 2, 2. So if I solve this, it tells me the system is inconsistent. So there's no solution. System is inconsistent. Now let's try the calculator just for the hell of it. 2 by 3, 3, -1, -4, -6, 2, 2. All right. So once it's in there, go back into the menu, go to REF, go back into matrix menu and pick the one you made. And notice this is how it looks like in the calculator. You see how it says 0 is equal to 1 in the bottom row. So that is inconsistent. That's false. If you see this on your calculator, you should say, oh yeah, there's no solution here. If you graph it and you see that's parallel, right away, no solution because the lines are parallel if you graph it. Anyway, is there any questions on these ideas here? Now this one has infinite solutions. Okay, so this one will be 2x minus 8y is equal to 4. X minus 4y is equal to 2. So let's go ahead and change it into matrix form first before we do anything. That'll be 2, 1, negative 8, negative 4, 4, 2. All right. Sorry, I'm distracted. All right, so let me show you what happens on the calculator. So if you try to solve this guy, go to second matrix, go to edit. What does it matter which one? I always choose the first one, unless I need to save them for something. 2, enter, negative 8, 4, 1, negative 4, 2. So that's all in there. Second matrix, REF, go get the one you made, pick the first one, that's the one I made. Now you see a row of zeros. So when you see a row of zeros, you say that's an infinite number of solutions. So if you were to do the work, I'm not going to make you just solve these by hand. Solving the matrix by hand is a real pain, which is really what the next section is about. But right now we're already solving matrices using our calculator and online solvers. So this means solutions. And over here, I'll go ahead and write got to write it earlier. It was 1, negative third, 0, 1, 0, 0. Okay, so you get a row. If you get 0, 0, and then equal to a number, that's no solution. If you get a row of zeros, you're gonna have an infinite number of solutions. Okay, and we graphed this guy, and we saw that they were on. Oh, we haven't yet. But we graphed this one. We saw they were parallel. So now let's graph this guy. See what that looks like visually. That is 2x minus 8y equals 4. X minus 4y equals 2. Okay, so let me share that. I forgot to hit share. So you see this black line and red line are on top of each other. So yeah, there's an infinite number of points here. So there's an infinite number of solutions. So system is consistent because there is a solution, but the system is dependent, meaning one equation depends on the other. They are not, they're basically the same equation here. That's what they mean by dependent system. Okay. Now let's use our online solver just one more time, a different way. Go back, set the matrix. So 2 for the x1 column, negative 8, oops, negative 8, 4, 1, negative 4, 2. See on this guy, it says that x2 is free. If you notice that it says this, then that's another hint that you have infinite number of solutions. All right. Let's take a small break. It's 7:58. Let's come back at 7:15, I guess. So earlier, again, these notes are in your Canvas. But at the very end, it shows you like what it looks like on the to call calculator, or when you solve it by hand. A matrix will have ones along the main diagonal here, and if that happens, then you have a unique solution, right? Exactly one. Row of zeros, like we said before, infinitely many. If you get some zeros and then a number, it's a false statement, so no solutions. Okay. Let's go ahead and move on to the next section. So that's pretty much 6.1 and 6.2. 6.4 and 6.5 are basically operations. And we'll do a couple examples, but so in this one, all they're going to show is how to add matrices. So basically you just go term by term. So this one is going to be added with that guy. So if I add, well, before we start actually, so if you add two matrices, they must be the exact same dimensions. So these are 2 by 2s, that's a 2 by 2. So if I add them together, it's going to be A plus W, right? That's the first. So the first terms together, the second terms together, B plus X, C and Y together, D and Z together. So just term by term. So now an example here, I don't want to spend too much time on this because it's pretty straightforward. This is a 2 by 3, and that is also a 2 by 3. These are the same size, same dimensions. So 3 plus 8 is going to be the first ones, right? -7 plus a -3. You add the negatives, so -10. 0 plus 4, right? So that's all you do. Entry by entry in the exact same location. So it's very easy to add a matrix. So I'm not going to really waste time on showing that. Here's another one, 3 by 3, same deal. 6 plus 7 is 13. 2 plus 2 is 4. 8 plus a -5 is 3. So that's all we're doing, adding the ones that are the same, in the same spot. And if you get ones that are not the same size, see how this is a 2 by 1 and a 1 by 2? Right away you just say not possible, or these matrices do not conform. So just there's no solutions, also fine. Okay, minus is going to be similar. It's just instead of adding each term, you subtract. So 7 minus a -3. So you write it down this way. 7 minus a negative is actually 7 plus 3, so 10. -2 minus 5, -2 minus 5 is -7. -5 minus a -3. Minus minus, that's plus 3. So -5 plus 3 is -2. -4 minus 4, -8. And that's pretty much it, really. Honestly, I don't want to. Do you have any questions about adding matrices? Is that self-explanatory or no? Is that weird? Okay, I'm assuming that it's not too bad. So that's addition and subtraction. Okay. There's some more concepts. There's more definitions. So if they ask for an additive inverse, that just means the negative version. For example, 7 and -7 are additive inverses of each other. -11 and 11 are additive inverses of each other. So A, B, C, D, right? You just switch the signs. That's the additive inverse. And when you add an inverse with its opposite, right? A value with its additive inverse, you will always get 0. But if it's a matrix, you get a 0 matrix. All of these are 0 matrices. They're just different sizes, different dimensions. So these are different from the 0 number. zero matrix. Okay. All right. I think that really matters. So the multiplication is a little more challenging. So let's do these a little slower. Okay. So we'll move on to multiplication. Do you guys have any questions on addition or subtraction? Okay. So we're going to start with multiplying a scalar. So multiplying a matrix by a scalar. Oh, crap. So basically, if you have a matrix, so here's an example. Let's say you have A equal to 1, 2, 3, 4, right? 5 times A, this would be the scalar. Basically, I'm scaling the matrix by, let's look at an easier, better number, because I can't write 5s. 4. 4A. So that means I'm going to scale the entire matrix by 4. So all you do is multiply all the numbers inside by 4. So 1 times 4 is 4. 4 times 2 is 8. 4 times 3, 4 times 4. So I scaled the matrix by 4. So that's all they mean by scaling multiplication. Okay, let me show you the examples in this note. So 3 times this matrix, so we multiply all these numbers by 3. So 3 times 2 is 6. 3 times 4 is 12. 3 times a negative 9 is negative 27. That's all we're going to do. Okay. Same thing here. Negative 6, you do negative 6 times negative 1, 6. Negative 6 times 0. Negative 6 times 4. Negative 6 times 2, etc. So nothing crazy. All right. Let me go ahead and show you. You don't really need to do this, but if you want to do it on your calculator, you can. Let's say you know what, I don't want to multiply by 4. So I can go in there, edit the matrix. This is a 2 by 2. 1, 2, 3, 4. 3, 4. Oops. So matrix A is in there. I do 4 times, and then I go get that matrix. So under names, just press enter to call it outside and multiply it. So 4 times that's right there. So I do negative 2 times the matrix. Go back in there and get it. It'll be negative 2 scaled on the matrix A. So you could do that with all these examples here. If you want to, you could just punch this in there times 3 or whatever. You don't really need to, because multiplying by a scalar isn't that hard, but if you want to, you can. Anyway, is there any questions about scalar multiplication? All right. So let's move on to multiplying rows and columns, and then multiplying 2 matrices together. So that's scalar stuff. So matrix multiplication. Let's start with product of a row matrix and a column. Okay, 1 second, sorry. All right, here goes another example. So we're going to multiply this row to -3 and 0 times the column -5, 2, and -2. So when you multiply a row by column, you do this entry times that entry, so that's how it works. 2 times a -5 plus -3 times 2 plus 0 times -2. So then you just add them together. This is -10 plus a -6, right? Plus a 0. So that would be -16. So that's how you multiply rows and columns. You do this times that one, this times this times this. It helps you write it out, because doing this in your head, you might make a mistake with the signs. It's not as easy as the scalar, so just be careful. Okay.
So in multiplying, it's always going to add together?
Yeah, you add each entry there. And that's how you also do the matrices, which we'll do next. Okay, so this time we'll do a matrix times another matrix. These can be a little bit annoying. I would suggest a calculator or something else, but let me show you how it works anyway, just so you can, you know, -1, -6, 10, 5, 8, -2. So in order to multiply, the inner dimensions have to match. 2 by 3, and this is a 3 by 2, right? 3 rows, 2 columns. So these need to match. So that's what I mean by inner. If those are different, you cannot multiply. It doesn't matter what's out here, the 2's. These 2's, though, will tell you the result. It's going to be a 2 by 2 from these 2. Okay. The way you do this is basically you create, I'm going to reuse up a whole space here, whole page. So you take the first row, 2, -3, 1, times the first column, and then you go to the next row or column. So use the same one. So I'm going to use this guy. First row times the first column, first row times the second column. So I'm going to write this down again, times the second column. Okay. Then I go to the next row. So -4, 7, 0. -1, 10, 8. Stay still with the same row. -4, 7, 0 times the last column, negative 6, 5, negative 2. Okay. Okay, you guys see where all these, where this is coming from, right? It's this row times that column, this row times that column. And then you go to the next one, that row times this column, and so forth. So then you just start multiplying, right? So we do, for the upper left corner, you do 2 times negative 1 plus negative 3 times 10 plus, what's the ugly 10? 1 times 8. And then you go to the, so that's the first multiplication here. This column, this row times that column, this. Now you do 2 times negative 6, negative 3 times 5, 1 times negative 2. Negative 4 times negative 1 plus 7 times 10 plus 0 times 8. Okay, negative 4 times negative 6, 7 times 5, 0 times negative 2. Okay, you guys see where all these numbers came from. I'm just doing this multiplication, right? Each of these. So all of this will become the entries for the new matrix. So you're going to get negative 24, negative 29, 74, and 59. They're multiplying, and again, like we said, that'd be a 2 by 2. So multiplying these two matrices, I will get a result of this. Okay? But you can see how that can be a little bit of a pain. It's not that fun. So doing that on your calculator, I recommend, if you have one. So now I'll see if I can find some solver. I'm going to create two matrices in here. So go to edit. First one is a 2 by 3, 2, negative 3, 1, negative 4, 7, 0. Now we go to the next one, 3 by 2, oops, negative 1, negative 6, 10, 5, 8, negative 2. So I've saved an A and a B. So I'm going to go back in there and press enter on the A, times, go back in there and select the B. And enter, and there's the results, right? Negative 24, negative 29, 74, 59. 2 by 2. This is a little easier. Let me see if that website can do it too, but let me check. Yeah, I think the same place can do it too. So here's the link again. Try it out on here. So the dimension of the first matrix was a 2 by 3. So 2 by 3 and a 3 by 2. Notice how I changed this one automatically because it's required to be the same. that matrix. So first one was 2, -3, 1, negative, -4, 7, 0. The next one is -1, -6, 10, 5, 8, -2. There we go. Calculate. Yeah, there it is. So you can use this too if you want. And that's what we got. You guys have any questions on solving these?
In the test where we show our work, do you want us to go through this whole thing, or can we just go to the 2x2 if we get it from the website?
Yeah, for the final exam, it will not require any work. I'm going to be very lenient. I just want you to pick the right choice. If you want to submit work because you're unsure, if you want to, if you're paranoid, you're welcome to it, but you don't have to. It won't require anything. Just do your best. I'm hoping everyone does well.
Thank you.
Okay, let me show you some more. Let me show some examples of where they don't match up. Okay. And again, you have these notes. I just wanted you to see them. So here's a 2x3 times 3x2, right? As we said, they would become a 2x2. So this row times that column is right here. This row times the next column, right? It's all there. And then this times the first column, just like we did on paper a few minutes ago. Over here, if you have a 2x2, the inner dimensions match. So the outer ones will be the result. Same deal. Here, if you multiply 3x3s, of course, you get another 3x3. This one, though, these inner ones are 2, but the outer is 3 and 1. So the result will be a 3x1. Okay, so I wanted to see how they result this way. But remember, if you see something like this on the test where they don't match, then you should just stop and say no solution, or in the calculator you end up getting this. You can say dimensions don't match, etc. Just make sure you know how to write the dimensions down, right? So always row by column. 2 rows for this guy right here, 1 column. So row, 1 column. 3 rows, 2 columns. Don't forget. Okay. Okay, that's pretty much it here for 6.4 and 6.5. You guys have any questions about these? We went through 4 sections, but as you can see, they're not too crazy when you have a calculator or a solver. I don't need you to understand the basic idea. That's all I'm asking for. Any questions about it before I move on to something else? Okay. The last 2 sections in this book is 7.1 and 7.2. I'm not testing you in chapter 6 and 7. I just had to remove chapter 5 and just focus on the final exam. But these questions will be on the final exam. So on Thursday, we're going to review everything on the final. But also, there's already videos posted So you can also look at those ahead of time or whatever, doesn't matter. But I'll make another video of our session too. Let me show you how 7-1 starts. It's pretty basic. So this is 7-1. This is graphing linear inequalities. So first they start you off like, hey, do you remember how to graph lines? I'm like, well, maybe, maybe not, but we have graphing calculators and websites, so who cares? But we know that if there's a slope, if the slope is positive, it raises this way. If the slope is negative, it goes downward, right? If it's y equal to a constant, it's always a horizontal line at that constant. If it's x equal to a constant, it's going to be a vertical line at that constant. So that's the stuff that we should already know, and I believe already talked about lines. But the new stuff, or I think maybe you have even talked about this too, was they changed the equals into inequalities. So they replace equals with greater than or greater than or equal to. But all that means is you shade a certain side. But I believe we can do that with our Desmos grapher. So let's go check it out. One second. Okay, so this guy, y is greater than x minus 2. So that's the graph we saw earlier. So basically, if it is a greater than symbol without the equal to, you get a dashed line. I believe we talked about this. And then you shade a certain section. So everything that's shaded is a solution to this inequality. It's no longer an equation, it's an inequality. Although, if it is, turn this one off. If it is greater than or equal to x minus 2, right? Oops, see how it's a solid line now versus the dashed? So equal to means we start right on the line and then we go everything above. This starts right after the line. That's why it's dashed. Okay. So I'm not going to make you graph these by hand. I mean, we already had a test on graphing. So you can use calculator or Desmos, not a huge deal. But this becomes important when you're doing like a optimization kind of problem. Let's see if I can find a cool question. So 7-1. All right, let's try this one here. Example 7. So on this question, they gave us multiple equations and they want us to graph it. So we can put all of these, this one and these two, into the grapher, and it'll create this region. Later on in the next section, we're going to create this shaded area and find out what is the optimal point in this area if this function represents like profit or something. Okay. So all these inequalities are really restrictions. So when real life happens, right, you can't build or sell infinite numbers of things. So we have to put restrictions. You have to say, okay, like if X is like, I don't know, burgers and Y is hot dogs, I have to have 0 or greater than, right? I can't have negative burgers. It doesn't make sense. So you should create restrictions on this stuff. And then 24 and 30 could represent your price. So $24 per burger, $30 per hot dog. Yeah, I know that's super high, but just an example because this is general. That's the idea. So you create this shaded region and you start to figure out, okay, if this was a business or whatever with multiple restrictions like time, number of employees, number of things I need to sell, and you put it all together, you'll find a section like this, maybe more complex, maybe more like this one. You start to think, okay, where should I? How many hot dogs should I sell, and how many burgers should I sell? So if you try to figure out what is the best combination to give me maximum profit, that's going to happen at the corners. So when you graph these things, you just pick the corners and test it. You plug it into the inequality here. Okay, but right now they're just showing you how to graph, but we can already do that using our grapher. So let's go ahead and try it. Right. Okay, so on this one, let's say doing number 7 from that PDF that you have, 24x plus 30y is greater than 7,200. Oops, 7,200. And then I put x has to be greater than or equal to 0. Y needs to be greater than or equal to 0. Zoom out. This top one is kind of big, so as you can see, the pink is starts at this line and goes all the way up. The purple starts at the diagonal and goes upward. Okay. Yeah, upward. And then you have the X, which is everything to the right of this black. Okay. So they all intersect together up here. So the region that has all the solutions is going to be up here somewhere. Let's double check. So all those, yeah. Now if we graph the other one, let's look at the other one. Doing these by hand can be real time consuming, so let's look at them. So the seed costs a farmer $40 per acre for corn and $32 per acre for soybeans. How many acres of each crop should the farmer plant if he wants to spend no more than $5,000 on seed? Express your answer as a linear inequality. So you need to label things, right? So X is going to be corn, right? And Y will be soybeans. So this is something you need to create. You just kind of decide. It doesn't matter which is which. You just label them. Once you do that, you're like, all right, well, $40 per corn, so that's going to be 40x plus $32 per soybean, right? 32y. And it said that I want to spend no more than 5,000. So this combination must be less than 5,000, where x is the number of acres of corn, y is the number of acres of soybeans. So what is the combination? Whatever combination you choose must be less than or equal to 5,000. Okay, and of course, x and y must be positive because I cannot have a negative corn, etc. So graphing all these, once you create them, will give you this region. So let's go ahead and try to graph them. Right? Okay, so if I go back to this grapher, delete all this. So the one you need to create first is the $40 per acre X plus $32 per acre of corn. So just choose another variable. Call it whatever you want. It doesn't have to be XY, but that's just what the book uses. And it says I don't want to spend more than 5,000. Then X must be greater than or equal to 0. Y must be greater than or equal to 0. Okay. Ready? Zoom out a bit. That's too much zoom. Zoom back in. Oh yeah, I was zoomed out from the last question. Okay. So this region right here is the feasible region. That's what the book calls it. So everything in this, these three colors are overlapping in one section. That's going to be this triangle. So you find where they all overlap, and then that's the region where your optimal amount will exist. So if this was your business, the maximum profit lives somewhere inside this little section. And the book has a theorem, and it's proven. It's a proof, right? That says that the maximum profit or maximum value of any function set up this way will happen at the corners, okay, or intersections. They all intersect here, so the only places to check would be the corners. So you would plug all these in. You plug into x and y into this equation here, or inequality. Well, I'm sorry, that's not true. If we were doing an optimization question, you would plug these 3 points into the profit function. These only help you find the points that matter. But I don't have a profit function for this example. That doesn't happen until 7.2. 7.1 just wants you to know, can you graph these guys by hand? Which I'm not going to make you do, so please use this grapher or your graphing calculator. Calculator can do it, but it's a little harder. I recommend using this, and I'll make sure that you're able to use these websites, okay? All right. You guys have any questions on 7.1? That's pretty much the big picture. Does it make sense? Like how you find how you graph them, or what it means? I guess we'll move on 7.2. If this makes sense, then 7.2 will be the same deal, but we'll be applying it to a profit function. And I don't want to waste too much time on this theory all that much. So if you're a business major, eventually this is going to come back up later, where the entire class is just about linear programming. So you'll see this again one day if you're getting your bachelor's in a business type of degree. So Z, they call it the objective function, which is usually in business the profit function. Okay. So the objective usually is to maximize or minimize the function, which we call Z. If it is a profit, well, of course, you want to maximize, right? If it is a cost type function, you want to minimize, depending what we're talking about. Let's look at this guy here, example 1. So it says, suppose that a college wants to rent several buses to transport students to a championship college football game. A large bus costs $1,200 to rent, and a small bus costs $800. So you got to choose a variable for the large bus and the small bus. Here they choose X and Y, and they say 1,200 times the X. That's where they got this from. 800 times the Y for small bus. That's what they said. 800Y. So then you get this objective function. But then later you'll apply restrictions to this, right? Because the college has to have, it's in the real life, right? You have to have restrictions on what you're doing. You can't just buy only one bus, or you can't buy infinite buses. You can't, whatever. So constraints is what I was talking about earlier in 7.1. So constraints was what we did a minute ago over here. Let me show you one more time. In this section, the constraints are going to be something like this. So these constraints are created with from within reality and the problem itself and what's required. Like if you're working for a business and they tell you we can only have 100 type of I don't know. Let's say we're doing construction, right? Let's say you can only have 50 plumbers maximum. You can only have 20 electricians, etc. And you know how much each one makes per hour, and you can figure out, okay, what are my restrictions and how many people allowed at the job site? That's another restriction. And you say, okay, how many hours of the day are they allowed to work? That's another restriction, right? We're only usually restricted to 40 hours because if you go beyond that, it's overtime, and that's a problem for a business because you lose a lot of money. So all these things will become constraints. And this question that we talked about earlier with the corn and the heck was it? Corn and something, whatever. Their restrictions, but they had to be positive because they were acres. So of course it has to be positive. And then they said that they wanted to spend less than 5,000. So you had 3 constraints. So going back to the bus question. That was the bus question. You're going to create the constraints. So this is how it works. So the number of large buses cannot be negative. Obviously, you cannot have negative bus or negative small bus. So X and Y are greater than or equal to 0, right? Large buses can carry 60 people and small buses can carry 45 people. The college must transport at least 3,600 students. So, okay, so that's a new restriction. Or actually, that's a new information. So large buses can carry 60, small buses can carry 45. So the first constraints is that they must be greater than or equal to 0, because you can have 0 large buses, but you cannot have -1 bus, large bus. 60 people for large ones, and X is large, so you get 60X plus 45Y. The college must transport at least 3,600 students. So the word at least means minimum of 3,600. So 3,600 or greater. In other words, greater than or equal to 3,600. That's how you read this. Okay. So that is created by this, by that information. Sentence C creates the C constraint. Now D, the number of available bus drivers is at most 75. So each bus needs to have 1 driver, right? Obviously. So the number of large buses, the number of small buses will determine how many cannot be, I guess the way to phrase this, right? If I have 75 drivers, then that means the number of large and small buses cannot be greater than 75. Because if I have 80 buses, I don't have enough people to drive them, correct? So the part D shows up by saying X plus Y is less than or equal to the number of drivers. So the number of large buses plus the number of small buses must be less than, but can be equal to 75 drivers. Do you see how all these constraints were created using this information? Is that clear or is that weird? Okay. All right, well, let's use information to graph it, and then we'll try to solve it without looking at the answer. Okay, go back to the grapher here. One second. All right. So they said that the number of large buses, x, must be greater than or equal to 0. That makes logical sense, right? Y must be greater than or equal to 0. Then they said that each bus, the large bus can carry 60, so a 60x, and the small bus can carry 45, 45y, and we must be able to carry or take at least 3,600 students. So I better not go below 3,600 because that would be a problem. That is a constraint that we were given, right? So like if you were planning this for like a big event, right, you have to make sure you don't spend too much money by getting nothing but large buses or nothing but small buses. You need to do a combination because the combo will give you the optimal price, right? So that's why we're doing this way. And then we said that the number of large buses plus number of small buses must be less than or equal to 75 bus drivers. So all of these constraints create a region called the feasible region. Let me make sure because all these colors are messing with my head. So black is going this way, red going this way, blue is going that way, green is going downward. So the section that I care about looks like it's right here. There it is. The feasible region is here because this is where all four colors overlap right there. Wasn't clear at first, but if you unhighlight them, you can kind of tell, right? Let's do one by one. So black's all right there. Red's up here. So now I know that it's somewhere in here. Blue is going that way, so now I know it's somewhere up here. Green goes downwards, so now I know that I'm restricted to here. Okay, does that make sense? I was able to spot this section. Okay, so now one of these three sections will be the optimal amount of large and small buses for the objective function. So you're going to plug in all three of these into the z function and find out what's the best one. And best meaning, well, it depends what they want, right? Let's see what they want. Okay, right objective function represents. Okay, yeah, there it is. Let me show you the question. Okay, so let's go back to the actual question here. So they graph it by hand, which is a real pain, but we already got these points. We already know what these corners are, thanks to the grapher. Corner points is 60, 0, which is right there. 75, 0, right? We already have that. And the intersection, technically you need to do some algebra to find it, but thanks to our grapher, 15, 60, it's right there. Now, the question will ask you, find the optimal number of large and small buses that will minimize cost. So you treat the z as your cost function, or the objective function that will minimize cost. So you basically plug in the three corners that we found on the graph into z and see which is the smallest. So here's the z, right? 1200x plus 800y. Plug in 15 for x, plug in 60 for y, add them together, 66,000. Do it again. Plug in 60 and 0, so 60, 0, add them together, 7,200. And then do the last one, 75 and 0. You get 90,000. So the minimum cost will be this section, 50, 60. Going back to the picture. 1560, not 50, is right there. So this is the optimal amount of large buses and small buses to make sure that I'm at the minimum 3,600 students or more. Do you see what this, how this works and why it's important? Okay. All right. Now let's look at the a little bit of theory here. And again, you have these notes already, but I do want to go ahead and talk about it. So the existence of optimal solutions. So if the feasible region for a linear programming problem is bounded, then both the maximum value and the minimum value of the objective function always exist. So in other words, if all of the constraints create a little section, then you are guaranteed a maximum and a minimum automatically. Now, if the region is not bounded, meaning it's not closed off and it just kind of goes on forever, then there is a minimum, but there is no maximum because it just keeps growing. So if we go back to that first graph, well, that was last time, up here. Something like this. See how it just goes on forever? Yeah, there's a minimum here somewhere, but there is no maximum because it grows. This one is closed off, meaning it is bounded. So a minimum and a maximum exist. Okay, that's what they're saying here. Oh, shoot. Close it. That's what they're saying on number 2. Where do you go? Here it is. B, rather. If the feasible region is empty, meaning all the sections do not overlap, then there is no maximum or minimum. So all the constraints need to overlap somewhere. Otherwise, you can't find an optimal solution. Okay. So in the homework, they'll probably give you a paragraph, or they'll start you off giving you something like this. So this is the objective, P or Z, depending on whoever writes it. You will graph all these pieces as your constraints, and then you find the corners. So then the corners just go into P, and then you find out which one's the maximum for this question. So the biggest one will be, actually there's 2 of them. So P can be maximized at 0, 8, or 2, 6. So that's all you do. Graph these guys, write down the corners, plug them into P, and then figure out, do they want a maximum or minimum? If they want a minimum, that would be the first one, right? If they want a max, well, you got 2 options on this question. I will not force you to graph this by hand because that's a real pain, but you don't have to. On this question, they all overlap somewhere, but it's not closed off, meaning there will be no maximum, but there is a minimum. So on example 3, they say find both minimum and maximum, but this one does not have it. So you would say, okay, minimum is one of the corners, but there is no maximum. Even though you have 3 options to choose from, and technically 56 is the biggest one, it does not make sense to say 56 is the max because I can choose any number way out here, and it will be bigger than 56. So there is none. There is no max if it is wide open like this. There will be a minimum. Again, with closed, there is a minimum and a maximum. Okay. Anyway, do you guys have any questions on these ideas? Does that make sense? I put in the chat box all the PDFs we were looking at. Okay, and also here is a instruction step by step on how to solve a matrix using a graphing calculator if you choose to do that. Do it that way, I mean. Okay, I'm gonna email them to you just in case you forget to download them. Notes from today. PDF notes. One moment. Okay, so I sent you the notes that are also in there just in case you lose them. You guys have any questions on what we talked about today? We will go over it again during the final exam review in case that was too fast or too much information. But you will see on the review, it's not too, there's not too much. There might be just like 2 or 3 questions on the final about these sections. There's not very many.
So the final is technically test 5, right?
There's not going to be a test 5. It'll just be 4 exams and then final exam.
Okay, and I guess I'm just looking at our lab. Do we have to do the 0.3 and 9.1 homeworks, or just the homework up to 7.2?
Just up to 7.2. I'm probably gonna I'll remove anything after that.
Okay.
What does it say what chapter 8 is? And I can't see here.
It says introduction to probability, and the 9.1 is probability distribution and expected value.
So let me check one thing before I make a promise to you. Hold on. Yeah, there's only one question in the whole final exam about probability. So we will go over it during the final review, and I will not make you do the homework for chapter 8.
Okay, and the final is over 6.1 through 6.5, and then 7.1 and 7.2?
No, it's over everything.
Oh, it's over everything.
Yeah, everything's from as soon as we started functions all the way till today.
How much time will we get for the final?
I mean, I can give you extra time. Let me see here. Currently, it's 3 hours. There's 18 questions, so it's not super long, but there is a lot of topics. But yeah, I'll give you 4 hours if you like.
Did you say 18 questions?
Yes.
Yeah, can we get a little more time, please?
Yeah, that's fine. It's not a huge deal. Let me do that right now before I forget.
And I'm sorry, I think you might have said this in the beginning, but I logged in a little late. Did you say it was due on Saturday? Saturday morning?
Yeah, Saturday morning. Because they want me to have the grades in by Saturday. So if I can wait till Saturday morning, the latest, and then I can start putting your grades in. I'll give you 300 minutes, which is 5 hours. You shouldn't need that much time, but at least that way you won't feel stressed. You guys have any other questions? Okay, one last thing. So I guess, and I don't know if people signed up for part 2, so they canceled it. So if you had enrolled in it, it's gone now. So sorry about that. There's nothing I can do at this point. I think we needed 5 people, but I think there was only 3 for whatever reason. But yeah, you'll have to take it a different semester if you need part 2 or somewhere else. Just a heads up. So if you need to take, if you want to take it in Flex 2, you should, I guess, start looking if there's anyone else offering it.